Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be drawing Feynman diagrams. Feynman diagrams are these pictures that we can draw that tell us the probability amplitude that some scattering process occurs. So let's begin. So in the last video, or the second to last video, on the Gelman-Low theorem, we derived this relation right over here, where S over here is a unitary operator evaluated from minus infinity to infinity, where here HI is just the interacting Hamiltonian. And we wanted to calculate this thing over here because this was proportional to the probability amplitude that some scattering process occurs. So the probability that, like, we have, say, two pions that enter our system and leave the system, something like that would be described with this correlation function over here, or is proportional to this correlation function right over here. And it shows up in the L as the reduction formula, which relates the S matrix to the correlation functions. So the weird thing is that these fields that show up here in the correlation function are in the Heisenberg picture. So these are the fully interacting fields, which are very hard to work with. So instead, we can use the interaction picture, which allows us to use the free fields instead, as long as we multiply by the S factor, and we divide by the same thing, sandwich between the vacuum states. And technically speaking, Hogg's theorem says that we can't really do this, but we just ignore Hogg's theorem and we just continue on. So for example, if we want to calculate 2-to-2 scattering, so say we had like two particles come in our system, so we had two pions with momentum k1 and k2, and they leave our system with momentum p1, p2, they have different momentum because they exert a force on each other because they interact. And that will be like represented with this right over here. We have two fields with x1, x2, and two fields with y1 and y2. If we had, say, 3-to-2 scattering, where we had, say, 3 pions come in and then 2 pions come out, that would look like a decay. So we have less particles coming out. That would mean that we'd have like 3 fields over here. So we'd have phi x1, phi x2, then like a phi x3 smudged in there, multiplied by these two fields. So the fields on the left, they represent the number of particles coming in our system, and the fields on the right represents the number of particles coming out of our system. And the reason as to why we have x1 and x2 here, and then y1 and y2, is because it's simply easier to use different variables for different particles because it's helpful to keep track of things. We could, though, in principle, write this out as x3 and x4 if we wanted to. So for the phi4 theory, we would have this over here for the unitary operator, because for the Hamiltonian of the phi4 theory, that's going to, the interacting Hamiltonian is actually going to be integral over the space volume of lambda phi4 over 4 factorial. And since for the unitary operator S, we should have t e to the minus I integral of dt of hi, well then we would basically just have another integral over time, or essentially the integral of dt of this is just going to be the integral over 4 space-time. And we use the variable a instead of x because we already have x being used here, so we don't want to use the same variable. So we are going to use a instead for the unitary operator. So essentially, if you want to calculate scattering amplitudes, it pretty much just comes down to calculating this thing over here. And how do we actually do that? Well, to calculate this thing over here, we can look at some things first. So we can look at the basic element of this over here. That's just going to be the Feynman propagator, the 2 points Feynman propagator, which is this over here. We know that it's equal to this over here, and we've actually calculated that in the video on propagators, and we also found the same thing in the video on field integrals. In that video, I actually didn't use I didn't include an I in the Feynman propagator, but there should actually be an I in there. Note that over here, we don't just have phi of x1 times phi of x2, we also have times phi of y1 and phi of y2. as well. So calculating this won't be enough. You have to calculate more general correlation functions. So for example, we can calculate the 3-point correlation function. We can do that by using path integrals. By using the path integral formula that we derived, we can note that this is going to be equal to this over here, where we would take the derivative of the generating functional 3 times at different points, and we would find out that that's actually equal to 0, because we're going to have an extra factor of j left over if we were to do the calculation yourself. So it turns out that any odd number of correlation functions are going to yield 0 for that reason. So we can calculate the 4-point correlation function, this over here, by doing the same gimmick as before. That's just going to be this over here, where here we have a product of those derivatives, but it goes to j of x4. And doing that, if we're to like run the numbers pretty much, you would end up with this right over here, where d of x1, 2, that's just the Feynman propagator, but between points x1 and x2. So like that would just be this thing, but we would have x1 minus x2 pretty much. That's all it means. So it looks like calculating the 4-point correlation function, we have to multiply Feynman propagator a bunch of different ones together, right? We talked about the details in the video on field integrals. And then we also have to note that the derivative of jx over jxk, this is the k by the way, equals the delta function of x minus k. That's how you would get this formula right over here. So here's the formula for the 4-point correlation function. So here's the 4-point function. For the 2-point function, t of phi x1, phi x2, we found that was just equal to d x1, x2. So here's the 2-point function. But for the 4-point function, it's much more complicated. So like say we drew x1 here, and here's x2, and here's x3, and here's x4. Here we have d of x1, x2 times d of x3, x4. So we have d of x1, x2, so x1 is kind of pairing with x2, and then times d of x3, x4. So x3 is being paired with x4. And we have a plus, and we draw the same thing again. We see that we have d of x1, x4, the Feynman propagator for the field between points x1 and x4. So that's this over here, times the Feynman propagator between x2 and x3. So you pair x2 with x3. And then plus this over here, getting it right, x1, x2, x3, x4. They have x1 and x3 being paired with x2 and x4. So this shows us that we are pairing x1 and x2 and x3 and x4 in all possible ways, it looks like. So here this represents d of x1, x2. Here is d of x3, x4. And this represents d x1, x2 times d x3, x4. And then this is just d x1, x4. This one is d x2, x3. And we're just multiplying those together. So all we're doing is we're just showing visually all the possible ways that these can connect to each other. And we're showing that this expression kind of has that. And we actually call these diagrams that we've just drawn right now, we call those Feynman diagrams. And you can actually see that these Feynman diagrams, what they just are, they're just telling us all the different ways that we can connect the points together. You would often hear people saying that Feynman diagrams represent like a physical process, right? Like in like QED, for example, a common diagram that you'll see is this one over here, where we have a photon, here you have an electron. This is, I think, molar scattering. You have two electrons scattering off each other. And you'd often hear people saying, oh, we have two electrons, they exchange a virtual particle, and then they leave the system. But these Feynman diagrams don't represent like actual physical processes, right? We haven't made like any like logical jump to saying that this represents like a particle moving from x4 to x3 or x3 to x4, all this is just a representation of this sum right over here. I say that because you often hear people saying the opposite, so I just want to clarify that. Sorry for the brief tangent, but let's continue. The time-ordered endpoint collision functions, which is this over here, is simply equal to all possible contractions. So what's a contraction? Well, we call, if we were to look at the 2-point function over here, we can say that we contract phi x1 with phi of x2 and get out the Feynman propagator between x1 and x2. For the 4-point function here, we can say that we contract phi x1, phi x2 to get d of x1, x2, and then we contract phi x3, phi x4 to get dx3, x4. Then we contract, say, phi x1 with phi x3, and then phi x2 with phi x4 to get dx1, dx3, and then dx2, x4. And hopefully you guys can now see what we mean by contraction. We define the contraction between phi of xk with phi of x, say, w, as the Feynman propagator between those two spacetime points. So what Wick's theorem tells us is to calculate the endpoint collision function, all we have to do is take all possible contractions and sum them together, technically speaking. So for example, say we want to calculate this right over here. So phi x1. So let's say we want to calculate the 3-point collision function. To do that, we have to take all possible contractions. So we can contract phi x1 with phi of x2 to give us d of x1, x2. But here we don't contract, we can't contract this with this as well. With Wick's theorem, it tells us that we can only contract 2 fields at a time. So we can't contract one field with 2 fields. We can only contract 2 fields together. So we can't contract phi x3 with anything, right? And as a result, this comes down to being 0, since phi x3 isn't paired with anything. But if we had the 4-point collision function, we could then contract it with this one over here. Let's say we have the 6-point collision function. So for the 6-point collision function, which we had to squeeze in there, Wick's theorem tells us that this over here is going to be equal to all possible contractions. So all possible contractions summed together. So let's look at a few of them. So we can contract phi of x1 with phi of x3. That'll give us d x1, x3. We can also contract phi of x2 with phi of x5. That'll give us d x2, x5. We could contract, say, phi of x4 with phi of x6. Well, that's the only possible one that we can contract. And we get this. Then it would be plus some different arrangements of contractions. So we can contract phi of x1 with phi of x2. That'll give us d of x1, x2. We can also contract phi of x3 with phi of x4. So x3, x4. We could also do x5 and x6. So x5 and x6. That'll be some different contraction. And then plus some sort of other configuration, and it just goes on. It's pretty long with higher order collision functions. I mean, basically, this is going to be equal to this over here, plus the other propagator functions. So Wick's theorem is pretty powerful because it allows us to take a complicated collision function, do some simple combinatorics, though it can be pretty hefty at times, and get out a simple answer as a result. So we can use that theorem to actually calculate this over here. Remember that the end goal is to find out what this thing is going to be. So let's actually do that. So first off, we want to find out what this is going to be equal to. Now to do that, we have to actually take the integral of the field raised to the 4th power over space-time, but it turns out that integral is not really possible to solve analytically. it turns out that it diverges. But what we could do instead is we could actually just expand out the time order exponential factor in terms of a Taylor series centered at x equals 0. I mean, that's what Taylor series means. But we would get what's to the right if we expanded it in terms of a Taylor series. Recall that a Taylor series for e to the x is just 1 plus x squared over 2 factorial plus over 3 factorial and so on. That's how we get this over here. And yeah, so we can just use the Taylor series to approximate this over here at just the numerator. So this means that just the numerator comes down to being this right over here. So here, this was just the factor te to the minus I blah blah. Okay, so important thing to note is that when we squared this integral, so remember that for the Taylor series, we have to square the second term or the third term, really, x squared over 2. Then we can think of this over here as being the x. So when we square it, you might naively think that we have to do like, it's just like this times this, which it is technically speaking. However, when we are dealing with integrals, if we want to square an integral, we do have to switch to a different integration variable when we square it, which means that we'd have this times this, and this will be a function of VB. So now what we can do is we can just distribute this part over here on the inside. And if we're to do that, we would get, so how do we actually evaluate this? Well, we can use Wick's theorem, right? So Wick's theorem, again, it says that the this thing over here, it's just going to be all contractions. So it's all contractions added together. So if you want to calculate the second order or the first and second orders of the Taylor series, oh, also some lingo, some physics jargon, we call this over here, this series over here for the unitary operator, we call that the Dyson series. That's just some lingo they might hear. So let's look at the first term over here. We actually already calculated what this was before. The first term is going to be dx1 x2 times d, like you guys already saw what it was before, right? So you don't have to go through that one again. Okay, we get that by just contracting these things together. In diagram form, the first order term is going to look like this. So you have x1, x2, and then y1 and y2 now. Ooh, interesting. And then plus x1, x2, y1, y2. But here they cross. I'm not going to write this out as a pure crossing. I'm going to write it out like more of an overlap. You'll see why I'm going to write it like that in the future, as in like 5 minutes. And then plus this over here, x1, x2, y1, y2. So these are the diagrams, and these are just this is just for the first order term. Okay, that's just the first term in this thing over here as a series. So for the second order term, things get a little bit complicated. We have the main thing that we want to find out is this over here. This is essentially an 8-point quotient function, but with different variables. So let's just try. We can contract this one with this one. That'll give us dx1, x2. You can contract this one with this one. That'll give us d of y1, y2. We can contract this one with this one. That'll give us daa. You can do this contraction. That'll give us daa. Okay, that's one contraction. For the second contraction, we can use we can go dx1 to y1. That's an interesting one. We can do phi of x2 to y2. Then again, we can have like daa. Oh, we can also try doing pair phi x2 with an a. So contract these guys together. So like this is one contraction. So dx2a. We can also do this over here, x1, y1. You guys get the gist of this. It's not very fun going through all the combinatorics. So we can just use the Feynman diagrams to kind of help us out here. So essentially we have x1, x2, same just as before, and then y1, y2. But we're not going to start like drawing these like random things here. No. Instead, we have an x for no. Instead, you have to notice here that we have 4 fields, and these are evaluated at the same point, right? So we could just draw like 4 more like points over here, and then we can just like combine them like crazy like this, but that's going to look very ugly. So instead, what we could do is we can actually, since they are literally the same point, you can just write them out at the same point. So here we have A, all connecting to the same point. And now what we can do is we can go, okay, here we have dx1, x2 times dy1, y2. So dx1, x2, that's this over here. dy1, y2, that's this over here. And then daa with daa. Well, if this is like, if each of these legs are one field, this is just this contracted with this times this contracted with this. So we end up getting this diagram right over here. And then for the second one, what do we get? So let me just write it out as the key. So here I have this one over here. For the second time, here we have dx1, y1. So x1 is going with y1. And then here we have x2 going with y2. And the same gist as before. This propagator, or this field goes with this field goes with this field. So the same thing, it's literally the exact same thing, but we just like rotated the vacuum bubble. That's what we call this thing over here. And then for this one over here, we have dx2, dx1 goes to y1, y2 goes to a, and then this goes over here. So this looks like this shrink, like that right there, in Feynman diagram form, where we just kind of like take this leg and like stretch it open. So that's it looks like that over there. And of course there are more of these terms that we have to add together, right? So to find these other terms, we could go through the contractions, or we can just use our intuition, right? We know that each contraction is just each possible configuration of the diagram. So that is basically means that what we could instead do is we could just like try to combine this diagram in a bunch of ways. So we could contract x1 with this one over here, x2 with this one over here, y1 with this one over here, and y2 with this one over here. That looks like this. Okay. And we have this vertex right over here. So another diagram that we can draw is this somewhere right over here. Now you guys might say, whoa, isn't this the same diagram as the one that we drew before? Isn't that this one over here? That's why we made this like overlap kind of instead of a pure crossing, because what this vertex means, if you were to actually picture it in your head, we have phi a to the 4 when we have minus I lambda over 4 factorial. So what this vertex means is that we should also include a factor of minus I lambda over 4 factorial. So before, right, when we did not have phi 4, so for the first order over here, that's why we do not use a pure vertex, right, over there. So yeah, for the second term, right, we would have 2 vertices. So we'd have to consider phi a times phi b, like literally 4 times, and that corresponds to having 2 vertices here. So then again, we could have like x1, x2. So again, this is for the second order. For the third order, we'd have y1, y2. Again, we could contract. So like here's like A, by the way. Here's A, here's point B. We could contract x1 with A, x2 with A, and then we could contract phi A with phi B, and then we could like do this over here. Ooh, we got this weird looking diagram. We call this a two-loop diagram. Is we could contract phi A with itself, phi A with itself again. Note, okay, each one of these legs represents a field at the same space-time point. So when we connect this with this, we're saying that we are contracting the field with itself. Okay, just to be clear, we're not just like doodling here. Like we're actually like doing something like mathematical, even though it doesn't really feel like it. So we can do this over here. We could do this over here. Okay, that's another one. Or what we could do, same gist. We can just do this over here. Another diagram that we can draw. We could do this. Looks like the eye of Sauron, sort of like it's like an evil eye guy over here, and he has like his hands or something. So we can look at that diagram right over there. A lot of diagrams that we can draw. Okay, there's a lot of weird diagrams that we can draw. So it turns out that you can probably see this yourself. The higher order terms we go in that series expansion, the more and more diagram possibilities we're going to have. We're going to have more and more vertices, so more possible contractions, which means longer diagram expressions. So what we've done here is we've derived what are called the Feynman rules. You may not have noticed it yet, but we've basically just done that already. We know that from Wick's theorem, the time-ordered quotient functions it's going to be equal to all possible contractions. Each contraction represents a propagator, and for each vertex we have to include a factor of minus I lambda over 4 factorial. So that's why for two vertices, we're going to have a squared over here. Each like leg, I guess, each leg / loop / like whatever you want to call it, gives us a factor of dxy pretty much. And then each vertex gives us a factor of minus I lambda over 4 factorial. And these are the Feynman rules for now. It turns out there's much more to it than that, but at least for now, that's what we have so far. So just to summarize, essentially what's on the numerator. Remember that there's a denominator that you have to divide by, but just looking at the numerator, we can expand this out in these Feynman diagrams. Here's going to be the first order contributions, and then here these are going to be second order contributions. Note that there are more diagrams in the second order contributions. I'm not going to draw all of them. Here's just a few of them. And then here are the third order contributions. No, not third order. This is actually 0th order. This is 0th order. And then this is first order. And then this is the second order contributions. Note that for the first order, we only have one vertex. So here's one vertex. Here's that one vertex. Here's one vertex. But for the second order, we have two vertices. That represents the fact that we have like the field squared at different points. So we have two vertices there. And each vertex will give us a factor of this over here. Now there is more to talk about. There are symmetry factors. There are some combinatoric stuff that you have to talk about. There's a lot more. So don't take the Feynman rules that we've derived at the end like fully, if that makes sense. There's still somewhere you have to address. But that's going to be in the next video. We're going to split this video into like 2 parts probably. So I'll see you guys then. So there should be a factor here. So yeah, so thanks for watching and have a great day. Bye.